All right. Um, radioactive spiders aside, let's begin. So, dear Father, we thank you for this day. Thank you for these students. Yes, you just bless this class today. Help us to glorify you what we do, Lord. In your name I pray. Amen. All right, let me get straight into it. Let's see here. And let's see here. Theorem. Last time, I proved a special case of the following. So I'll just start with this. For t, a linear transformation from v to w. All right. We have the following. One, if v naught is a subspace of v, then t of v naught is a subspace of w. And point number two, if w naught is a subspace of w, then the inverse image under t of w naught is a subspace of v. So last time I proved this theorem for the special case that, I proved this theorem last class actually for very special cases, all right? So like, what was the special cases we looked at last class? So like t of v equals the image of t, and that is a subspace of the codomain w. All right? And in this particular case, the thing I looked at last time was if we look at v naught equal to the trivial subspace, then kernel t is the inverse image of the zero subspace, and that is the subspace of the domain. All right? So like, we looked at those. I actually proved this theorem for those special cases last time. But truth be told, we could easily modify the proof that I gave to prove that, in fact, the image of any subspace is a subspace, and the inverse image of any subspace is a subspace with respect to a linear transformation. Now, keep in mind that in 2, I'm not saying that the linear transformation is invertible. This is a function theoretic statement, all right? That's the inverse image of w naught under t. It doesn't mean that t inverse actually exists as a function, all right? One of the things I want to do today is to try to give you a description of when it is that t inverse exists as a function. Like when is a linear mapping invertible, all right? So let's work our way towards that. The next thing on my list of things I should share with you is just a kind of reminder. So let's see here, reminder by L of VW. What do we mean by this? It's the set of linear transformations from where to what? Right, from V to W. Now, notice that that is technically a subset of the function space from V to W, right? Because a linear transformation is a function with a rather particular set of skills, right? I mean, it's linear. But it's certainly a subset. And we can define, right? If you let, if I have t and s in linear transformations from V to W, then we can define t plus s of x, and we can define c times t of x. We did this before, right? The sum of linear transformations is defined pointwise like this, right? The scalar multiple of linear transformations defined pointwise like that. But the interesting theorem is that if t and s are linear transformations from V to W, and C is in the field of scalars. So here I'm assuming that V and W are vector spaces over some field F, okay? So if you have a linear transformation T, a linear transformation S, and both from V to W, and if C is a scalar, then guess what? You can prove that CT plus S is also a linear transformation from V to W. So if I take two linear transformations and I add them together, or I scalar multiply them, I get another linear transformation. So what does this say? What does this mean then? This theorem I just wrote. What is that? What's the import of that for the set of linear transformations from V to W, like L of VW? What's this say about that? So if I have this theorem, right, and I have this observation, what else do I need? Oh, yeah, okay. So, yeah, if we put 0 of x equals to 0 for all x in V, and that's the 0 in W, then you can check that 0 is an element of the linear transformations from V to W, which is non-empty. So what am I getting at here? Subset satisfies sum and scalar multiple is again in there. It's non-empty. We can use the subspace test to prove that, in fact, so the result I'm getting at here is simply this. Linear transformations from V to W are themselves forming a vector space of a subspace, rather, of the function space from V to W. In other words, this is a vector space in its own right. Like, is there anything that's not a vector space? Well, yes, there are things that are not vector spaces. Don't worry. I'll show you one. Okay, so further theory here. Theorem 7.1.26 says something rather interesting. T, a linear transformation from V to W, is, I'm butchering the grammar here, if T from a linear transformation from V to W is a bijection, then T inverse is a linear transformation from W to V. Yep. Yes, we had math 200, so we know what a bijection is. A bijection is a one-to-one and onto map. So the proof here is as follows. So assume T is linear. And T is one-to-one and onto, all right? In other words, it's a bijection, right? Then T inverse from W to V exists, right? So if we have a map, if we have the mapping as one-to-one and onto, then we can define the inverse map, right? This is just set theory. So let x and y be in W and C a scalar. Consider. All right, so I want to show that T inverse is linear. All right, so here we go. T inverse of Cx plus y. I'm going to try to do both 1 and 2 of the definition at once, right, using this 2-for-1 check like we've been doing. So how do I get my hands on T? I mean, I only know that T is linear. I know that T inverse exists, right? How can I convert Cx plus y to something involving T? What do I do? Use the definition one-to-one onto. That's one option, sure. How about this, though? What if I were to do T t inverse of x. Would this make sense? Can I take t composed with t inverse of x? Would that be a meaningful thing to do? I mean, what is t composed with t inverse? By assumption, it's the identity map, right? So t inverse of t inverse of x is equal to x again, right? So this is an identity which is available to us because the inverse of t exists. And I can also do this for y. What would be the advantage of rewriting the expression in this way? Why did I do that? See, because now I'm in the position that I can use the linearity of t, right? I can use the linearity of t to rewrite this as follows. This is t of c, t inverse of x, plus t inverse of y, by linearity of t. All right? But then what can I do? Then I can use the definition of the inverse map in t again to cancel the t composed with t on the outside, right? Like t inverse of t of the inside is just the inside again, right? So I can just drop the t composed with t inverse. In other words, these two guys cancel, much like an exponential and a log, right? And that just leaves us with c t inverse of x plus t inverse of y, which is precisely what we need to show. Now, you can contrast the way I did the proof here in class to the way I did it in the notes, and you can see which you think is better, okay? I did not do the proof this way in the notes. I did it in a more sort of verbose way. You see what you like more, but I think this is a good argument for proving this. This is actually, like, surprising, all right? Because in general, when you look at a function and it's invertible, right, the inverse function doesn't have to be the same kind of function. For example, why this is a little bit surprising. If I had f of x equals to x squared for 0 less than or equal to x less than or equal to 1, to find the inverse function, I can set y equals to x squared, solve for x, and I get x is the square root of y. See? That's f inverse of y. So as you can see, the function is a square function, but the inverse function is a square root function, right? They're not the same kind of thing. They're different kinds of things. But if we have a function's linear and it's invertible, that forces the inverse to be linear again, right? It's a very nice, special thing about linear transformations. Now, up next here, this is a very, very important theorem. This one we actually use a lot. A theorem given t is linear, all right? T is injective, it's 1-to-1, if and only if the kernel of t is 0. So this is theorem 7.1.17, if you're keeping track. Many, many times I have asked for the proof of this on a test, and here it's very, very common. I think it's a good test question because it's not that hard, and it really shows me if you understand the concept of what a one-to-one function is, what the kernel is, and you can make, you know, basic biconditional kind of arguments. So let's go here. Forward implication. Suppose t is linear and suppose t is 1-to-1. Right? Observe t of 0 equals to 0. Therefore, 0 is in the kernel, right? And what does that mean? Well, of course, the 0 set is a subset of the kernel, right? This is silly. True. I want to prove that they're equal, right? So to prove that the kernel is equal to 0, I need to show the only thing in the kernel is what? Just the 0. So like let x be in the kernel of t. Then what? What's that mean? T of x is equal to 0, right? But what's 0 also equal to? It's also equal to t of 0, is it not? Hence what? By one-to-one property of t, we find x equals to 0. Therefore, kernel of t is just 0. That's the forward direction. Notice we needed the one-to-one in order to make that argument go, right? What does one-to-one say? It says that if t of x is equal to t of y, then x must be equal to y, right? Here I'm using y is 0 and, well, x is x. All right, other direction. Other direction. So assume what? Assume the kernel of t is 0. Suppose x and y are in the vector space V with what? T of x equals to t of y. Then t of x minus t of y is equal to 0, hence t of x minus y is equal to 0. So if I assume t of x is equal to t of y, I can argue that t of x minus y is 0. But what does that say about x minus y? If t of x minus y is equal to 0, what does that say about x minus y? It says that, but why does it say that? First of all, what does it say logically? What does this say about x minus y? I mean, I agree with you guys. No, I mean, yes, but in between that, logically, x minus y is an element of what? The kernel, right? That's how you guys know it's equal to 0. Because what are we given here? We're given that the kernel of t is 0. So if x minus y is in the kernel of t, that means x minus y is equal to 0. Which then gives us what you guys were claiming, which is x equals to y, right? And that proves, of course, that hence t is 1-to-1, right? And that completes the proof. Again, this is special, right? This is really, really special to linear transformations. An example of a nonlinear transformation for which this is not true, let's look at f going from, say, the reals to the reals. F of x equals to x squared, you know? If you were to calculate the kernel of f, meaning x in the reals, such that f of x equals to 0, what would that give you? Which, yeah, I mean, exactly, just 0, right? Because the graph is this, right? But is this function 1-to-1? No, it is definitely not. In fact, the inverse image of, of a is equal to the square root of a, it's equal to, square root of the absolute value of a, oh, good grief. It's equal to the square root of a, minus square root of a, comma square root of a, right? For a greater than 0. And the inverse image of b is just equal to the empty set if b is less than 0. In other words, the fiber of this map, the inverse image of a singleton, it's only just one thing if it's 0. Like the inverse image of 0 is just 0. Only 0 maps to 0. But if you draw a horizontal line through the graph, any other point, you hit 2 points, right? So like there are two, So this is like A. This is square root of A. This is minus the square root of A, you know? This theorem, in some sense, is what it's saying. If you really get down to it, it's saying that the fiber of a linear transformation has the same size. But anyway, I'm digressing. We'll get back to that when it's time. Let me shut up about that. I have other things to say today, more important things. Okay, so eventually, let's see here. Trying to be disciplined here and not digress. All right. Next bit of theoretical linear algebra that we need to cover is if we have T as a mapping from, let's say, V to U, and S is a mapping from U to W, both linear, both linear maps, let's say, because I'm sick of writing transformation, then guess what? The composite of these, which order should I make them, which order should I compose them in here? How about S composed with T, which would be a mapping from what? From V to W, is also a linear map. So in other words, the composite of linear transformations is again a linear transformation. Let me actually prove this one for you, okay? So we should look at S composed with T of, let's say, Cx plus y. All right, and to be clear, I should say let x and y beware. Sorry, my font size is very small at the moment. Where? Reals? No. What's the input for T here? V, right? And C is from the field of scalars, F, whatever we're working with here. So I'm assuming U, V, and W are all vector spaces over some given field F. I'm sorry, I didn't write that out. Okay. So if I look at S composed with T of Cx plus W, what is that? By definition, that is S of T of Cx plus W, Cx plus Y. That's the definition of composite, right? Talk about the composition of maps in Math 200. And then T is linear, right? So this means that S of Ct of x plus T of y we can write. Since I'm assuming that T is is a linear transformation from V to U. But what do you know about T of x and T of y? Where are T of x and T of y? T goes where? They're in U, right? And what is S? S is linear where? It's a linear transformation from U to W, which means I can break up the sum that's being fed to S, right? Because we're giving a linear combination of vectors in U, and by linearity of S, I can pull the scalar out and I can break across the addition. And therefore, what do we got? Well, this is C times S composed with T of x plus S composed with T of y, which then is C S composed with T. Oh, well, there, I'm done. That shows that the composite is linear, right? Because I just showed you can pull a scalar out and you can break across the sum. So the composite of linear transformations is a linear transformation. Now, Any questions? Um, advanced calculus. So it would be when I would study nonlinear transformations, maybe a little bit in this course. I mean, I throw in some here and there, mostly the same example. Y equals x squared gets us a long way in terms of seeing what's different, you know. But I should mention, what's an algebra? What is an algebra? Yeah, an algebra is a vector space paired with a multiplication. So a multiplication, this general idea of a multiplication is, it's some way we can multiply two vectors and get another vector. All right, so what are some examples of, like, what's a simple example of an algebra? How about this? If we take R3 with the cross product, so we could, you know, if you give me a vector A and you give me a vector B, we map it to A cross B. So the multiplication is something like, you know, going from the vector space across the vector space to the vector space again. This is the multiplication. It takes in pairs of vectors and outputs a vector, right? The cross product does this. So R3 paired with the cross product is an example of an algebra because, well, it is. Now, but it's a kind of weird algebra because it's a non-associative algebra. Like A cross B cross C doesn't make sense. I don't know if you know this or not, but A cross B cross C is not equal to A cross B cross C in general. Cross product does not work like this. In fact, the cross product satisfies a particular sum of these things being 0 called the Jacobi identity. So actually R3 paired with the cross product is an example of what's called a Lie algebra. All right, just a point of fact for you. But what's a more interesting example is if we look at linear transformations from a vector space to itself. All right, I called these the endomorphisms last time. Is an algebra with respect to composition of linear maps. In other words, if you give me S and T, both linear maps from V to V, right, then the composite is again a linear map from V to V. By the theorem we just proved. So linear maps on a vector space to itself form an algebra with respect to the composition of linear maps. Another example of an algebra which is interesting is matrices. You can either add or multiply matrices and get another matrix of the same. We're talking about square matrices, right? So like the product of square matrices is a square matrix. You know, the sum of a square matrix and another square matrix is a square matrix. So a third interesting example would be, say, Rn by n is an algebra. Okay. And so the notation for this algebra usually used is GLV. So little GLV is the set of, and you got another notation for endomorphisms of V, all right? In contrast definition, big G LV would be the subset of little GLV big GLV contains only invertible linear maps. All right? So big GLV is the set of, this is also known as the general linear group. The general linear group on V. It's the set of invertible linear transformations on V. I told you eventually I'd talk about something that's not a vector space. Well, this is not a vector space. If you take two invertible linear transformations, right, will the sum of them be an invertible transformation? I mean, we'll take a linear transformation and take it and subtract itself, right? Like, is the zero map an invertible transformation? It is not, right? What do you need for the linear map to be invertible? What would it take for T to be in GLV, by the way? Can we say T from V to V invertible, let's suppose it's linear, all right? Means two things, right? We need that the kernel of T is 0, and we need that T of V is what? Is V again. See, this gives us 1 to 1, and this gives us onto. We need both of these things in order for T to be an invertible map, right? So if you look at arbitrary linear transformations on a vector space, that won't be the case for a lot of them. I realize this is getting a little bit abstract. Let me try to bring it back down to earth here and talk about linear transformations on column vectors for a little bit, okay? Because that's kind of a happier place for you guys. So we'll talk more about what it means for T to be in big GLV later, okay? Let's talk about if T so I need to pick up a few pieces I left out here. If T goes from Fn to Fm, right? What was that? And S goes also from Fn to Fm, right? And if C is a scalar, then guess what? Number one, the standard matrix of T plus or minus S is, you guessed it, the standard matrix of T plus or minus the standard matrix of S. Point numero 2, wait a minute, numero dos, what am I wrong? What's wrong with me? Standard matrix of C times S is C times the standard matrix of S. So like the standard matrix of a sum or difference or scalar multiple of linear transformations is just what you kind of expect. What's surprising, though, is the following. If we had T going from, let's say, Fn to Fm, and we had S going from Fm to Fp, then S composed with T is a mapping from Fn to Fp, and guess what? The composite, the standard matrix of the composite is the product of the standard matrices of S and T. First of all, we've proved in general that the composite of linear transformations is linear, right? So we already know that S composed with T is linear. So all that really remains to prove, my last statement, let's call it 3. All that remains to prove 3 is just a calculation, right? So let's prove 3. Because I think it's instructive. So what is the standard matrix of S composed with T? What was our definition? It is S composed with T of E1, S composed with T of E2, S composed with T of how many columns? n? Sure. I feel like that was a guess, but you got lucky.
We use n a lot. So.
We use n a lot. N is it's a good guess, right? But yeah, n is the dimension of the domain here, right? So E1 through En are the basis for the domain. So we feed those in, that gives us the n columns for this matrix. Now, by definition of composite, that is S of T of E1, right? All the way down to S of T of En. But then what? By definition of standard matrix, that's the standard matrix of S times T of E1, the standard matrix of S times T of En, right? Remember that we have that S of V is equal to the standard matrix of S times V by construction of the standard matrix for S, right? So that's true for V. It's also true for like T of E1, T of E2, T of En. Then what? Remember we had the concatenation proposition? So if you got like the same matrix multiplying each column like we do, we can pull that matrix out, right? Remember that homework problem? We can pull that matrix out like so. And what is that? Well, that's nothing more than the standard matrix of S times the standard matrix of T. And in fact, one way to look at this in retrospect is that we defined matrix multiplication precisely as we did so that this would happen. So that the matrix of a composite would be we could just multiply the matrices of the transformations being composed. So this is, I know, to me this is a very nice bit of matrix algebra. There it is. I have a homework problem about this, of course, but so let's collect our thoughts. So concerning T, a linear transformation from, say, Fn to Fm. All right. First of all, we have that T of x is the standard matrix of T times x, right? For all x in Fn. And I make the following observations. Number one, the kernel of T is, in fact, equal to the null space of the standard matrix of T. My second observation is that the image of T is, in fact, equal to the column space of the standard matrix, right? My third observation is that T is invertible. What? If and only if n equals to m, and the dimension of the null space of T is equal to 0, and the dimension of the column space of T is equal to what? 0 would be wrong.
Is it a letter or a number?
Is it a what?
Is it a letter or a number?
Is it a letter or a number? Ahem. So let me put it this way. In order for T to be invertible, we need that it's 1 to 1, right? That means that the kernel has to be 0. So for this to be, this equals 0, right? If and only if T is 1 to 1, right? It's one of the things we learned today, is that the mapping's injective only if the kernel is 0, right? And it's surjective only if what? T of Fn equals to Fm, right? For T onto. In other words, for T to be onto, we need that the column space actually gives us back all of Fm. But if n equals m, that means that the dimension of the column space has to be n, right? Remember, we have the rank nullity theorem. What's the rank nullity theorem say? It says that n is equal to the dimension of the null space of the standard matrix of T plus the dimension of the column space of the standard matrix of T. But that also says the dimension of the kernel of T plus the dimension of the range of T is equal to the dimension of the domain, which in this case is Fn. This rank nullity theorem is going to be true for linear transformations over abstract vector spaces, but we'll get to that. I'm just stating it for column vectors at the moment. So if you want to check if a linear transformation of column vectors is, one-to-one or onto, you need to think about what's the null space, right? If the null space is 0, right, and the column space is as big as the, if the null space is 0, it's one-to-one, right? If the column space is as big as the codomain, then it's onto, right? If it's both of these things at once, it must be that the domain and the codomain had the same dimension. They're both Fn is equal to Fm, and in that case, it's invertible. What else could you say about the case it's invertible? What would we have if n equals m? It's a square matrix, right? So what would you think would be true about the standard matrix of an invertible linear transformation? What simple thing could we check to calculate whether or not it was invertible? The determinant, right. The determinant of the standard matrix would be non-zero if the linear transformation was invertible. Okay?
So because all the points will map on to basically a line, and squish all space down to like a plane or something. So we can reverse that.
I think one-to-one means that
But the determinant wasn't.
well, so, some examples. We could have t of xy equal to like x0y, or we could have t of xyz equal to xy. I think these examples, let's see here. So here, t is 1-to-1, but not onto. So you can calculate that the kernel of t is just 0 for my first example. In my second example, this t is onto, but not 1-to-1. So I don't know, like the kernel, to me, if the mapping is 1-to-1, that says it's like preserving lines or planes or whatever the domain supports. So this is a two-dimensional domain. So like it would support either lines or lines through the origin, that's pretty much it, or the whole plane, whole xy plane. And I mean, this is essentially pasting those onto, if I was to foolishly try to graph it, what y is equal to 0, and this is x, and this is z, right? So it's like basically taking the xy plane and plastering it on the xz plane. That's what the example 1 does. In contrast, this one, it takes like three-dimensional space, right? And it just smooshes it. So if you pick any point down here, like x, y, 0, viewing that as a subset of R3, which of course is a slight abuse, but then, like above that, there's this whole, line which is getting smushed to that. In other words, t inverse of xy is equal to what? So the fiber of a point in this example is a whole line, and that's also as big as the kernel. The kernel here is one-dimensional. So what's going on is a combination of these ideas, I mean geometrically, but I shouldn't have answered your question, now I'm behind. But it's a good question.
Just helps to visualize it.
Sure. So where we're going with this is I'm trying to give you a good collection of what we know about linear transformations, all right? So linear transformations are very special in terms of the structure I've shared with you today. But it's more than just that. So we have a definition. I mean, the thing I haven't shared with you today is what linear transformations do to linearly independent sets. Right, so the theorem I didn't get to write out on the board today, but I'm just going to say, is that if a mapping is one-to-one, all right, linear mapping is one-to-one, then it takes a linearly independent set and it maps it to a linearly independent set. On the other hand, if the mapping is linear and we look at the inverse image of a linearly independent set, it's automatically linearly independent. So certainly, if we have a linear transformation, which is also one-to-one and onto, right? It's going to like map a basis to a basis is the bigger point I'm making here. So like a bijective linear transformation will map a basis to a basis. All right. So that's a very nice result. And that is useful as we discuss the following definition. If V and W are both vector spaces over F, and then we say V is isomorphic to W, if there exists, let's say, psi going from V to W, which is a linear bijection. So two vector spaces are said to be isomorphic if there exists a one-to-one and onto linear map from one to the other. And furthermore, because of what I just told you about linear transformations, what could you tell me about the dimension of V and the dimension of W? If a linear map takes, if a linear bijection takes a basis to a basis, if it maintains linear independence and spanning, what does that say about the dimension of isomorphic vector spaces? Right, they should be the same. So, as we'll discuss next time, isomorphism of vector spaces actually forms an equivalence relation. So any vector space is like isomorphic to itself under the identity map. If you have V is isomorphic to W, then W is isomorphic to V, because you can just look at the inverse of the isomorphism and it's an isomorphism. All right. By the way, this map psi is called an isomorphism of vector spaces. And then we also get transitivity of the equivalence relation because the composite of linear transformations is a linear transformation, and if we compose invertible maps, we get an invertible map. So that means that isomorphism is an equivalence, isomorphism of vector spaces is an equivalence class where we can label each equivalence class by the dimension of the space in the finite dimensional case. So like there's an equivalence class of 3-dimensional vector spaces, or 2-dimensional vector spaces, or 4-dimensional vector spaces. In other words, what this is ultimately going to say is that up to a choice of notation, an n-dimensional vector space over F is really just Fn, right? So we've looked at kind of weird different examples, 2x2 matrices, polynomials. What I'm saying is, in some sense, as far as the linear algebra is concerned, they're really just column vectors in disguise, right? So that's where we're going. Anyway, I'll shut up. I think that's all I got for today. You got it?